Hi there, welcome to the channel, and today we'll just be covering the basics of Kirchhoff's voltage law. And I'll just be going through a little interpretation to help you visualize and understand Kirchhoff's voltage law for yourself. And to show you how it works, we'll be solving a few problems afterwards. So let's begin by discussing KVL, Kirchhoff voltage law. KVL states that the sum of voltages around the closed loop in a circuit is equal to 0. So if we were to use KVL to analyze a circuit, we should really consider what affects the voltage in a circuit. So let's take a look at a voltage source. This is a voltage source for a single cell battery. Now, while we use conventional current for circuit analysis, and it is very good for that, but within a voltage source, the current flows from a negative to positive potential. So we can say that this provides a voltage, and if the current flows in opposition to this, let's say the current flows that way, we can say this subtracts a voltage. This opposes the principles for a voltage source. And we also have resistors that will always resist the flow of current. And this is the equation for the voltage drop across a resistor using Ohm's law, because the current will drop across a resistor, so therefore the voltage will follow suit and also drop. So this will also subtract the voltage. Now, covering these three principles of voltage effects on the circuit, we can assume that the sum of all these is equal to 0 in any circuit. So let's start by having a look at some problems to solve. For this circuit, what I want you to do is to find the total current that flows through the circuit, find the voltage drop across R1, R2 and R3, and therefore verify KVL for this circuit. Pause the video if you need to and start solving the problem. So the first step is to sum up the equivalent resistance. If you want to practice summing up resistance in series or parallel, I recommend you watch my first video where I introduce you to series and parallel circuits. So back to the solution. 4 plus 6 plus 10 is 20 ohms. And we want to get the total current. So I equals V over R. 10 over 20 is 0.5 amps. So now we have the total current, we can find the voltage drop across R1, R2 and R3. So for VR1, it's 0.5 times 4 is 2 volt drop. VR2 is 0.5 times 6, that's a 3 volt drop. And for VR3, it's a 0.5 times 10, that's a 5 volt drop. So now that we have all this, we can find the expression for KVL. So I'll start writing it here. 10 volts minus VR1 minus VR2 minus VR3 equals 0. Because VR1 is 2 volts, VR2 is 3 volts, and VR3 is 5 volts. That sums up to 10 volts, therefore verifying KVL for this circuit. For this problem, what I want you to do is to use KVL to find the total current in this circuit, and then with that current you can then find the voltage drop across each resistor and therefore obtain a full expression for KVL, completing the problem for this circuit. Take your time if you need to and pause the video. So let's start by solving this circuit by using KVL, because we know following KVL that everything in this circuit is equal to 0 by summing up all the equivalent voltages. But in this circuit, V1 and V2, they oppose each other because the current will both flow this way and it will flow that way from V2. But take note that 12 volts is greater than 3 volts. So we can write this in terms of 12 minus 3. And then we can write 6 times I, which is the voltage drop across R1, and 3I, voltage drop across R2, is equal to 0. And this can be simplified easily. 9 minus 9I equals 0. And move 9I to the other side, so add 9I to both sides. And therefore, 9 over 9 was 1 amp. And that is your total current in this circuit. So now we have the total current. We can find the voltage drop across each resistor. In this case, it's just 1 amp, so it's going to be 6 volt drop across R1. And for VR2, it's going to be 3 volts. So, calling back to the first expression here, and just insert the numbers. Oops. 12 minus 3 minus 6 minus 3. So that is V2, V1. Oops. That is VR1. And that VR2. Sorry, this is a bit untidy, but this is the solution. That verifies KVL for this circuit. For the last problem, what I want you to do is to find the total current flowing through this circuit, the voltage drop across R1, R2, and R3, therefore obtaining a full expression to verify KVL. Take your time if you need to and pause the video. So the first step to solve this problem is to write a KVL expression for this circuit that can be rearranged to find the current that flows through the circuit. This time we have two voltage sources again, but however, they are flowing in the same direction. The current from the voltage source flows in the same direction, so they can add to each other. We can write it this way, 10 plus 15, that's V1 and V2, minus the voltage drop across R1, minus the voltage drop across R2, minus the voltage drop across R3. They all equal 0. So rearranged, or rather simplified, we won't rearrange it yet, 25 minus 23I equals 0, which can now be rearranged as 25 is equal to 23I. And to finish this, 25 over 23, divide both sides by 23 to get this, you get the current, which has a value of 1.087 amps. And that's your total current there. So now we have the total current, we can now find the voltage drop across each resistor. So let's start with R1. VR1, voltage drop across R1 is 1.087 times 6 equals 6.522 volts. That's the voltage drop across R1. For R2, similar case, 1.087 times 5 equals 5.435 volts. Oops. And for R3 finally, 1.087 times 12 equals 13.044 volts. That is your voltage drops there. Now, to finish this up, let's get the KVL expression. So just plug in the numbers really, because that's the voltage drops here and there. So 25 minus 6.522 minus 5.435 minus 13.044 equals 0. And that is your KVL expression for this circuit, and that's the problem solved. Alright, that wraps up the video. Thank you very much for watching. I hope you enjoyed and learned something new, and I'll see you next time.